Welcome to part 1 of the video on soil structure. This video examines soil structure, starting with its basic definition and genesis. Soil structure is the arrangement of primary and secondary soil particles, or aggregates, into a particular pattern. Primary particles bond together to form these aggregates, which are often called secondary particles. Good soil structure, like healthy soil, allows for better water infiltration, aeration, and root growth, compared to degraded soil with weak structure. The genesis of soil structure involves two main processes: flocculation, followed by the cementation of floccules. This diagram illustrates the concept of zeta potential and how it relates to particle interaction, which is key to flocculation. Flocculation is an electrokinetic process. Clay particles with a high zeta potential repel each other. Adding a flocculating agent like calcium or magnesium lowers the zeta potential, allowing particles to attract and form floccules. The second process is cementation of floccules. This consolidates the clay floccules with cementing materials, such as inorganic oxides or organic matter, preventing their dispersion and leading to aggregation. This illustration shows the components involved in soil aggregation, including clay flocks, water, cations, polysaccharides, and alpha hydroxides acting as binding agents. Soil aggregates form on a scale from micro to macro aggregates, involving clay, silt, organic matter, microbial debris, and plant roots. Soil aggregates are constantly being formed and disrupted, with organic matter and biological activity playing critical roles in their formation and stability. Aggregates are broadly categorized into two types: structureless and aggregated. Structureless soils include single-grained, dominated by sand particles, and massive soils, typical of compacted clays with no visible pores or cracks. Both restrict plant growth and water infiltration. Aggregated soils have distinct aggregates, or PEDs. They are characterized by their type, which is shape and arrangement, class, which is size, and grade, which is distinctness and durability. The type of aggregate structure includes plate-like, prism-like, block-like, and spheroidal. Classes are very fine to very coarse, and grades range from structureless to strong. Plate-like structures have more developed horizontal dimensions and are characterized by horizontal cleavage planes. They restrict infiltration and aeration. Thick units are platy, and thin ones are laminar. Prism-like structures have a more developed vertical axis, appearing column or pillar-like. They have predominant vertical cleavage planes. Prismatic tops are angular and flat, while columnar tops are rounded. Block-like structures have equal dimensions, resembling a cube. Angular blocky structures have sharp edges and corners. Subangular blocky structures have rounded faces and edges. Both offer good drainage and root penetration. Spheroidal structures have all axes equally developed. Granular structures are less porous. Crumb structures are highly porous and well-suited for agriculture, promoting infiltration and root penetration. This image shows examples of different soil structures, including granular, blocky, platy, massive, and single grain. This slide is for classification reference for soil structure classes. In platy structures, the class relates to thickness. Fine structures are thin, and coarse structures are thick. Grades are qualitative classifications based on the stability of aggregates, which is their resistance to disruption. Stability is influenced by moisture content, clay type, cations, and organic matter. The grades include structureless, weak, moderate, and strong. Weak structures are poorly formed, while strong structures are very well developed, stable, and distinct. When describing soil structure, the sequence is grade, then class, then type. For example, a description might be strong coarse angular blocky or moderate thin platy. Soil structure results in the formation of different sized soil pores. Therefore, soil structure can also be defined by the arrangement of these pores in a specific pattern. Macropores, larger than 0.06 millimeters, are essential for aeration and drainage. Micropores, smaller than 0.06 millimeters, are crucial for water retention. A well-aggregated clay soil has a good balance of large aeration and drainage pores and small water retention pores. Good soil structure features small or medium aggregates with abundant pores both within and between them. Porosity is influenced by texture and structure, as well as indirect factors like organic matter, bulk density, and management practices. Total porosity varies from 30 to 45% in sandy soil to 45 to 60% in clayey soils. The distribution of pore sizes is more important than total porosity. Sandy soils have larger, more uniform pores and lower water-holding capacity. Clay soils have smaller pores, higher total porosity, but may be poorly drained. Water retained at low suction depends on capillary effect and pore size distribution, which are strongly influenced by soil structure. Water retention at high suction is mainly due to surface adsorption, influenced by texture. Soil compaction decreases total porosity by reducing the volume of large interaggregate pores. This decreases water content at low suctions, but intra-aggregate micropores remain unaffected, keeping high suction water retention similar to aggregated soils. Soil structure significantly affects water flow. This influences how water infiltrates, percolates, and is retained within the soil. Soil aggregate stability measures the aggregate's resistance to breaking apart from forces like water, wind, and tillage. It's an indicator of soil quality, combining physical, chemical, and biological properties. Aggregate stability directly impacts pore size distribution, affecting water and air movement. Soils with good stability have a mix of micro, meso, and macropores, leading to higher total porosity and better water retention and air movement. A mix of pore sizes is vital for root penetration and microbial health, as oxygen is essential for aerobic organisms. Good aggregate stability increases water infiltration, reducing ponding and improving root access to nutrients. Let us explore the factors influencing the formation and stability of soil structure. We will focus on physical, chemical, and biological factors. Physical factors include wetting, which increases the pressure of entrapped air, breaking large clods. Rapid water entry into dry clods causes unequal swelling, leading to fragmentation. Drying causes shrinkage, and alternate wetting and drying form smaller aggregates, especially in fine-textured soil. Freezing is another physical factor that causes cracks in large clods due to the expansion of water. These cracks enlarge upon thawing and refreezing as they take in more water. Chemical factors involve exchangeable cations and binding materials like clay. Clay acts as a cementing agent, and its swelling and shrinking help hold small aggregates together. Soil organic matter is the main binding agent in soils, with 2:1 phyllosilicate clay minerals. Exchangeable ions also play a role. Divalent cations like calcium and magnesium have a flocculation effect, forming floccules and binding particles. Conversely, sodium ions cause dispersion, hindering aggregate formation in sodic soils. Hydrated sesquioxides form irreversible colloids upon dehydration, helping to create stable aggregates, particularly in lateritic soils. They also form complexes with humus. Calcium carbonate, when precipitated around soil particles, acts as a cementing material, improving aggregate stability. Soluble salts also enhance the flocculation of clay. Organic compounds like fats, waxes, lignin, proteins, and resins are key for aggregation. Humus forms clay humus complexes, but only calcium humus is flocculated and contributes to aggregation. Soil organic matter can be classified as transient, persistent, or temporary. Temporary organic matter stabilizes macroaggregates, while transient and persistent organic matter stabilizes microaggregates. The role of organic matter in aggregate stability can be complex to determine. The role of organic matter in aggregate stability is limited. Only a portion of total organic matter contributes, and there is a threshold above which more organic matter will not improve stability. Also, it may not be the primary binding agent in some soils. Synthetic soil conditioners, which are long-chain organic compounds, are also used for soil aggregation. These polymers bind clay particles together, and small additions can significantly improve the structure, even in sandy soils. Biological factors are critical in soils lacking shrinking and swelling properties. Soil organisms have both indirect and direct effects on aggregate formation. Macroaggregates are held by roots and fungal hyphae, while microaggregates are bound by persistent organic bonds. Plants and their residues help bind soil particles. Gelatinous organic compounds from roots and root hairs penetrating clods aid in creating aggregates and granular structure. Roots and fungal hyphae are important, temporary binding agents in early aggregate formation. Roots provide exudates for soil organisms and can dry the soil. Fungal hyphae stabilize macroaggregates and secrete polysaccharides for microaggregation. Plant residues feed microbes, which produce sticky substances upon decomposition, forming humus that binds particles. Microorganisms like algae, fungi, actinomycetes, and bacteria bind soil particles more effectively than exchangeable ions. Soil fauna, including rodents and insects, break down organic matter, create tunnels, bind soil particles, and mix soil layers. They also affect the microbial community. Small soil fauna, through burrowing and mixing organic residues, facilitate aggregate formation. Earthworms increase structural stability through casts and flocculation. Microarthropods also improve soil structure via fecal pellets. Agricultural management practices significantly impact soil structure. Tillage disrupts aggregation by exposing subsoil and increasing decomposition. Reduced or zero tillage and the use of cover crops improve soil aggregation by increasing organic matter and soil cover. Perennial crops prevent aggregate disruption through reduced tillage and extensive root systems. Organic matter inputs like mulch and manure increase aggregation by adding carbon and boosting biological activity. High livestock stocking rates can decrease aggregate stability due to compaction. Soil conditioners are amendments that improve soil properties, like structure and water retention. Examples include gypsum, compost, and biological amendments. For effectiveness, they must be applied correctly and are often site-specific. Climate affects aggregate stability through precipitation intensity and amount, which can increase erosion. Higher temperatures accelerate decomposition, reducing carbon and aggregate stability. These influences interact with soil type, wetting/drying, and freezing/thawing cycles. Soil structure is evaluated using two primary methods, direct and indirect. Direct methods assess the shape, size, and arrangement of aggregates. Indirect methods measure aggregate stability and related soil properties. The microscopic method, a direct technique, involves examining thin sections of soil under a petrographic microscope to reveal the nature, shape, and size of secondary particles and voids. The macroscopic method involves dropping a dry soil chunk from a height onto a hard surface. The resulting fragments reveal the PD sizes and shapes, which determine the type of soil structure. Indirect methods include measuring aggregate stability, the resistance of aggregates to dispersion. The stability index, which compares particle sizes from mechanical analysis and water suspension, is one way to evaluate this. The structural coefficient is another indirect measure, calculated using the percentage of small particles from mechanical analysis and wet sieving. Higher values indicate better soil structure. The dispersion coefficient and water drop method are also used. Soil structure can also be evaluated by measuring related soil properties. These include bulk density, infiltration rate, hydraulic conductivity, aeration, available soil water, and the degree of compaction. The size distribution of stable aggregates is determined using dry or wet sieving. Dry sieving assesses stability against vibrating action, indicating susceptibility to wind erosion. Wet sieving determines the size distribution of water-stable aggregates. The Yoder apparatus is used for wet sieving. It's well suited for separating aggregates smaller than 0.1 millimeters, though a lower limit of 0.25 millimeters is often more satisfactory. Aggregates are sometimes treated with alcohol before wetting to prevent destruction. Indices of soil structure use a single value to compare structural status. Common indices include mean weight diameter, geometric mean diameter, log standard deviation, change in mean weight diameter, coefficient of aggregation, and the percentage of aggregates larger than 0.25 millimeters. Mean weight diameter is a commonly used index. It estimates the weighted percentage of average sizes of all aggregates. Soils with an MWD greater than 0.25 millimeters are typically considered good for crop production. The change in mean weight diameter takes into account stability under both dry and wet sieving. A smaller difference between the two MWDs indicates a better soil structure. Soil structure influences nearly all plant growth factors, including water supply, aeration, and nutrient availability. Strong aggregation reduces runoff and soil erosion. It's also vital for soil classification and is affected by management practices like tillage and fertilization. Soil structure is impacted by agricultural management through factors like heavy machinery, raindrop impact, and foot traffic. Compaction and repeated tillage, especially when the soil is wet, also negatively affect the structure. To manage soil structure, tillage should occur at optimum moisture levels. Adopting minimum or zero tillage reduces organic matter loss and erosion. Soil surfaces should be covered with crop residues and organic matter incorporated for stabilization. Integrated use of organics and maintaining adequate calcium levels also helps. This scene highlights the management of soils experiencing structural problems. There are specific management techniques needed for soils with structural issues to restore optimal conditions. The dispersion of clays occurs when repulsive forces between negatively charged particles are strong. Monovalent cations like sodium enhance this mutual repulsion, leading to dispersed particles and small pores. This significantly reduces water infiltration. Thank you for watching this video on soil structure.